Good morning to all of you. In the last lecture, we have talked about the viscoelastic materials and the modeling of the viscoelastic materials. In this lecture, we will focus on the application of viscoelastic materials, because after all in this course we have to see how this will be important in terms of the basically vibration control of a system. Now, in order to do that, there are some more things that we have to keep in our mind. One is called the so called glass transition temperature of a viscoelastic material, the complex elastic modulus of viscoelastic material, and we have to also understand the frequency and temperature dependence of such material. And finally, once we have a good knowledge of this, we will come to the point of application of viscoelastic material. So, that is the journey that we are going to make today. Now, stiffness and damping in comparison to all other materials, for viscoelastic materials, both stiffness as well as damping, they are actually frequency and temperature dependent. So, which means that when you are applying a dynamic load, and if you remember that single degree of freedom system, right. So, if I just draw that single degree of freedom system for your reference, this was the Kelvin-Voigt model of the viscoelastic material, let us say, and we have a mass here, and this is the viscoelastic material K and C, which is subjected to some kind of a dynamic loading F bar e to the power j omega t. Now, while finding out the response of this system x, which is also something like x bar e raised to the power j omega t, while finding out this response of the system, we have to note down that this k and c both are actually function of omega, that is the excitation frequency, as well as temperature, as well as theta, which is the temperature. Theta is the temperature for us. Okay. So, our life will be more complicated, because the constants you usually treat in Kelvin-Voigt model these two as parameters, stiffness and damping, as the constants, but now they are no longer constant, they will be function of temperature and the function of frequency. Now, why does this happen? First of all, let us try to look into that. This happens due to transition from glassy to rubbery phase. These viscoelastic materials, they have a certain kind of a configuration, and that configuration is very sensitive to dynamic loading as well as temperature. So, glass transition temperature is something which actually works like a watershed, that before glass transition there is some kind of a behavior, and after glass transition there is some other kind of a behavior. In fact, if you look at that, what happens for a liquid to crystal formation is that if you kind of keep a cooling process, which is a control cooling process, then most of the metals and metallic oxides go through this route, that you will develop a crystalline solid. Whereas, if you have a very fast cooling process, or if it is a viscoelastic materials etc., then you will not see any remarkable change in terms of the specific volume at this point, rather it will as if behave like a liquid, and then beyond this point this solid like behavior will appear, which is the glassy behavior, and this is when the crystals are not forming. This happens because this structure is amorphous in nature. That means there is no well defined crystal structure that will be able to be formed in this structure, and that is true for the viscoelastic materials also, that if you look at their even in a solid form, we call the glassy form, if you look at that phase, you will see that it has totally amorphous structure. And from the glassy phase, as we increase the temperature or as we decrease the frequency, either of it, we will go to the rubbery phase, and while going these there will be a transition. That transition is known as the glass transition temperature. So, below this glass transition temperature Tg, the material will be very much hard and brittle like glass, and this is mostly due to the reduction in the motion of large segments of molecular chains, because those chain motions will be frozen, because they will not get enough activation energy. And beyond this you will get the rubbery behavior. Now, this temperature is of course different for each viscoelastic material. For example, if you think of polyethylene, your common plastics, it is minus 110 degree. That means the way you use a plastic bag at that phase, it is not at all in a glass state, it will be in the rubbery state. Okay. Now, same thing is true for polyethylene, high density, polypropylenes, etc. Nylon on the other hand at room temperature is actually at the glassy stage, because 57 degree nylon gets changed. Polyester also 69 degrees, so in room temperature they are also in the glassy stage. Same thing is true for the PVC and all these materials. So, some materials at room temperature are actually at the glassy state, these are these, and some material at the room temperature are actually at the rubbery stage. So, this is different for each viscoelastic material, and this happens the glass transition only to polymers in the amorphous state. So, the question now is that how can we define the modulus of elasticity of a material, because it is undergoing such a change. Well, we have the generalized stress strain relationship, which I earlier said as generalized Hooke's law. We have that with us, that model, if you remember, which we have used for obtaining the material parameter. So, in that model, if I write it in longhand, then it is A0 sigma, A1 sigma dot, A2 sigma double dot, etc., that equals to B0 epsilon, B1 epsilon dot, B2 epsilon double dot, etc. Now, you imagine that I am giving either a forced harmonic excitation, which will produce a harmonic stress, or I will give a harmonic strain, either of them. If I give a harmonic stress, that let us assume that is resulting in a harmonic strain. So, if I apply back these two in the equation above, what I am going to get is that since e raised to the power j omega t will be cancelled from both the sides. So, we are going to get this kind of an expression, okay, in terms of stress. You have sigma 0 is the amplitude of the stress. Okay. So, A0 sigma 0 plus j omega A1 sigma 0s, etc., etc. And similarly, here if you apply it here in epsilon, you get B0 epsilon 0 plus j omega B1 epsilon 0 plus j omega square B2 epsilon 0, etc. So, you can take sigma 0 common here, and you can take epsilon 0 common in the other side, and you can write the expression of sigma 0 over epsilon 0, which will be something like B0 only this term, then j omega B1, then j omega square B2. So, that is what will be our numerator, plus of course, if you want to go, this is a series. And similarly, here you have A0 plus j omega A1 plus j omega square A2, that is what is our denominator, plus some additional terms if you wish to go. So, what does this means? It means that our numerator is a complex quantity, because you have this imaginary part in it. So, it is complex, as well as our denominator is a complex one. So, this sigma 0 over epsilon 0, let us say if it is after all it is stress over strain, let us say I denote it with an Young's modulus E star, which now I know is complex because my numerator is complex, my denominator is complex. So, let us say this E star is actually having a E prime, which is the real part, and E double prime, which is the imaginary part. So, E prime is the real part. We often call it as the glass modulus or storage modulus, and E double prime we call it as the loss modulus. So, these are the two parts that are there in the complex expression of the modulus of elasticity. Now, we can also find our old friend loss factor now with this definition, because E star is E prime plus J E double prime. E star E prime I told you is the storage modulus, which is the measure of the stored energy and it depicts the elastic behavior. On the other hand, E double prime gives you measure of the heat or energy dissipated, the viscous behavior. The loss factor is defined as the ratio between these E double prime over E prime, and it is also written in the form of a tangent, because it is in the real versus imaginary plot, right. So, you consider real of E or E prime, that is what is our E prime, and imaginary of E star, let us put it rather, okay, that is what is my E double prime. So, basically if you want to locate a particular point, you have this pair of coordinates here. Okay. So, you have E prime as the real modulus and E double prime as the loss modulus, and this angle here, the delta, is expressed as tan delta. This is nothing but your E double prime over E prime. That is what we have noted in this, that is a kind of a geometric expression. So, this this loss factor here is something that we are getting back. If you remember earlier, we have discussed about loss factor, and you can apply actually these equations to get the same loss factor back. I will leave it as an exercise for you. Okay. Now, if you actually look into the basic expression of E star, now E star is E prime plus J E double prime. So, what is our J? So, what is our J E double prime? E double prime is nothing but E prime tan delta, right. So, that means E star is nothing but E prime into 1 plus of course, the J is here 1 plus J tan delta, and tan delta is eta. So, that is what we have written here, that E star is E prime into 1 plus J eta. Now, that is for the Young's modulus. Similarly, the shear modulus can be derived as G prime into 1 plus J eta, assuming that the loss factor is same in all the cases, bulk modulus as B prime into 1 plus J eta, and the relationship between the Young's modulus and bulk modulus and shear modulus as E star as 9 B star G star over 3 B star plus G star. So, thus we can actually get the modulus of elasticity of the system. Now, once we know these delta, tan delta, etc., this delta value, what is the range of it? Okay, it goes between 0 to 90 degree, and as delta approaches 0 degree, you have a purely elastic behavior. So, in such a case, what you may see is that the material does not show this kind of phase transition at all, okay, if delta becomes 0 degree. On the other hand, if delta approaches 90 degree, then you get a purely viscous behavior, and the glass transition is where this dramatic change is happening to the system. Now, if you really look at it, that a polymer at this stage, it is like a long chain of the polymer, and all this main chain of the polymer, it may have some side chains also, as I told you earlier. So, everything remains frozen because of the low temperature, but around this point onwards, the polymer may actually get itself mobilized in this kind of a form. So, you get a crank like motion, and that means a lot of mobility comes into the polymer, and that is why such a sharp decline in terms of the real modulus starts to take place. And also because of this decline, lot of energy is getting wasted. So, you get a sharp peak in terms of these the loss modulus of the system. So, this is the kind of material explanation of what happens to the system. Now, let us try to summarize the behavior of viscoelastic material with respect to frequency and with respect to temperature. So, with respect to frequency, if we look at it, we will see, or maybe it will be easier first if we first look into it with respect to temperature, that at the low temperature this is your glassy phase and here it is brittle, yet it is having a high modulus of elasticity. But as the temperature increases, this motion increases and there is a sharp fall in terms of the shear modulus. Now, frequency behaves just the other way around. That means, whatever is good or whatever happens in a low temperature, you will see that is going to happen at a high frequency level, and whatever happens at a high temperature, that is going to happen at a low frequency level. What does it mean? It actually means that if the dynamic excitation that you apply to a viscoelastic material, if it is very low, then the system actually gets enough time to self adjust itself. So, all the motions are possible, and as a result of that, that means in a low motion scenario you get a low modulus of elasticity, because it behaves like a flexible material. But if the frequency increases like in this direction, then the chains do not get enough time. They say something like noodles, they get actually confused, they get jumbled up, and as a result the modulus of elasticity increases. So, that is what happens in this particular case, as you have seen the behavior of the shear modulus with respect to temperature and frequency. Now, as far as the loss modulus concerned, it always happens at the transition period. So, that means nothing much before that or after that, but at the transition period where suddenly you have lot of energy dissipation possible, then these things happen, and this happens not only for frequency but also for temperature. For temperature, we call it to be theta critical, which is your glass transition temperature, some people call it Tg, and here you call it a critical frequency omega Cr, where this kind of a phenomena you will be able to see. So, this exercise you can do that with this model. You try to use this your earlier definition of eta, which is energy dissipated in a cycle over maximum potential energy of the system during the cycle, and then you will see that you will get a kind of a expression of E star, which will conform to this expression as well. So, now we know how this material behaves in this manner. Now, let us see that what are the applications of this viscoelastic material for particularly keeping vibration control in mind. Well, there are huge applications. I have subdivided them into three parts: additive layer, where viscoelastic material is applied as an additional layer. So, let us say this is what is my structure, which is vibrating, and I am applying a small layer of viscoelastic material. So, this is an additive layer, and this additive layer in this case is a free layer, that is I have just added it on top of it. It may happen that on top of these I actually give another layer which is constraining the viscoelastic material, then it is constrained layer damping, CLD. It may happen that on top of these I am actually applying another layer which is actually a smart material layer. So, this is a smart material. In that case, we will get something which is known as active constrained layer damping, or ACLD. But these are all layer wise treatments. Viscoelastic materials can also be used as inserts, for example, in joints or in surfaces. One example could be that you have one part of the system, and then you are actually having another part of the system coming up. So, you are joining the two. So, you have something like what we call a top hat stiffener composition. So, this is where the viscoelastic materials will be given, okay, because this is a joint of the two layers. So, you are going to get viscoelastic materials here in this part. So, as inserts. Similarly, it is also used in surfaces. Now, viscoelastic materials are also used in a large way for the isolators like rubber springs. It can be a free spring, it can be a bonded spring. In case of a bonded spring, you can have something like a viscoelastic material, and in two sides you have the metal casing which is bonded with it. So, you can have this kind of a situation, and the bonding between the two could be either mechanical or it could be chemical. So, there are so many applications of viscoelastic material that is possible, you know. So, it is really very good in terms of vibration control. Now, let us look into a few of them. I will just give you the overall results of them. One is, as I told you, that unconstrained viscoelastic material, and the other one is constrained viscoelastic material. So, these are all damping layer type. So, for unconstrained viscoelastic material, say for example, you have a plate here and you have a viscoelastic material completely unconstrained, free to deform. In this case, the energy is generally dissipated due to the extensional deformation of this viscoelastic material, which is undergoing an extensional deformation. The expression for this loss factor can be written in terms of the height ratio and the modulus ratio. Height ratio is h2 over h1, that is this ratio of the thickness of the base layer and the viscoelastic layer, and also the corresponding modulus of elasticity ratio. You will see that this is the way it actually you will get the expression. In fact, if you neglect all higher order terms, then what will happen, your eta E2 will be approximately eta E2 times, let us say I neglected all the higher order terms. So, 3 EH over 1 plus 3 EH, that is what it will be. So, essentially what it means is that this is one factor which will be less than because this 1 plus 3 EH is there, your denominator is more, unless E2 over E1 ratio is actually very high, you will not gain much out of it. So, in order to get a high loss factor, suppose in terms of this kind of a simple application, either you should have a large eta E2, that is one thing that you can have, and the other possibility is that your E2 over H1, of course H2 over H1 you will never try to increase this, because then there will be a weight penalty. Okay. So, you will actually not be able to do that, but E2 over E1, where E2 is the viscoelastic layer modulus of elasticity and E1 is the modulus of elasticity of the base layer. Now, let us say that your E is very small. So, you can actually write this expression in a slightly neat manner. Suppose if I write it here, that it is eta E2 times, let us say I divide top and bottom. So, it will be by 3 EH. So, it will be 1 over reciprocal of 3 EH plus unity. So, if I get small EH here, so if I get a large value of E2 over E1, so if this part increases, the numerator will increase. So, if the numerator increases, then the denominator will actually the overall reciprocal will actually come down. So, that will not have a good effect for us, but if E2 over E1 difference is actually very small. Okay. So, in that case what will happen is that this small ratio will be much larger in the reciprocal part in comparison to unity. So, then this will be the dominating part. So, if there is a large difference of modulus of elasticity, and then if this becomes the dominating part, then with eta E2 it will have a reciprocal effect. That means, the overall damping will get sacrificed very much. So, we have to judiciously choose the modulus of elasticity ratio of the system. Now, constant layer damping is a little bit different from the free layer damping. As you can see, this is an aircraft where these constant layer dampers are actually utilized. So, here you have a constraining layer, and hence that bending of the flex, or so to say the flexural expansion of the viscoelastic material is not happening, rather what is happening is a kind of a shear that will happen. Now, viscoelastic materials are generally very much responsive to shear kind of a thing. So, hence more energy dissipation is possible in this manner, and that is why constant layer dampers are generally much better in comparison to the free layer damping. So, they actually exceed the extensional damping of that you find for the constant free layer damping situation. Now, if the extensional stiffness of the viscoelastic layer is negligible in compared to the stiffness of the bottom and the top layers, and that is what usually you will find in the real life, that viscoelastic material would not have much of a extensional stiffness, but will have a much of a shear, is kind of sensitive to shear. So, then the overall loss factor, you can neglect the extensional damping, and then it will be you can neglect the damping due to extensional stiffness. That is what is extensional damping would mean. Then you will get it in such a manner that the overall loss factor will depend on eta G2, will depend something called the YG, which is actually a kind of a parameter, is called the stiffness parameter, okay, that you will get, and also you will get a shear factor G. So, there is a shear factor G which will come into picture, and eta G, and the parameter Y, which is the stiffness parameter. So, this is the definition of the stiffness parameter that you will find, okay, and the shear parameter is actually defined by this relationship. So, here once again you will see, for example, for the stiffness parameter, you will see that the ratios that are important here is the stiffness ratio of E3 over E1. That means the modulus of elasticity of the constrained layer with respect to the modulus of elasticity of the base layer. So, naturally, if the higher is the value of E, you will see that it may increase the value of Y, and as a result you may get a higher loss factor. So, we try to always get a kind of a constraining layer which has a very high modulus of elasticity. I mean, something like people say jokingly that diamond is very good as a constraining layer, as a thin diamond layer, because you always look for a very high stiffness material. Now, if you look at the other factor, that is the G parameter, then you will find that here the storage modulus of the viscoelastic material plays the major important role, and the more is the storage modulus G, then that is going to affect your overall loss factor. So, this parameter G itself. So, this is how this whole thing behaves in terms of a constrained layer system damping. Now, you can also make, because the shear damping is actually much higher than the flexural damping. So, you can try to enhance this shear strain by actually artificially constructing a system in which you keep this entire viscoelastic layer and the constrained layer away from the neutral axis of the system by developing a kind of a extension corrugated kind of a configuration. So, this is one way of doing, and another approach is of course to make a sandwich construction where the original member is divided in two equal halves with a viscoelastic layer inserted between them. So, we try all these different types of technologies in terms of having more shear in the viscoelastic material and thereby generating more loss into the system. So, this is where we will come to an end as far as the application of viscoelastic material is concerned. In the next lecture, we will talk about dynamic vibration absorbers and a model of a simple vibration neutralizer. Thank you.